Yes, sir. Thank you, sir. Hello, everyone. My name is Gautam Arora, and today we are here to talk about laser optical communication in deep space. And my co-author on this was Rajat Kumar and Dr. Sudhir Kumar Chaturvedi. Now, when we talk about laser optical communication in deep space, we first need to understand what we mean by deep space. And the deep space means space well outside the Earth's atmosphere, and especially that part lying beyond the Earth Moon system. And why do we need communication there? Well, firstly, if we want to go to Mars and become an interplanetary species, we will need some good communication system to communicate back to our home planet Earth. And also, we have many missions beyond Mars. They are beyond Jupiter. Some is beyond Saturn also. And they all transmit data back for analysis. And day by day, the amount of data is increasing. And the need for faster communication and better quality signal is increasing. So that is why we are here to talk about on that topic. But why laser communication? Why not we just go by the conventional means? But firstly, they have greater signal strength by power ratio. Secondly, better signal quality. They are less costly. They have low maintenance, low loss for greater distances. We can also use pulse signals. They are immune to interception, and they have exceptionally large bandwidth. Laser communication will enable us for 10 to 100 times more data transmitted back to Earth than current radio frequency systems. It would take roughly 9 weeks to transmit a complete map of Mars back to Earth with current radio frequency systems. But with lasers, it would take about 9 days. Additionally, laser communication systems are ideal for missions because they need less volume, less weight, and less power. Less mass means more room for science instruments, and less power means less of a drain of spacecraft's power system. These are all critical important considerations for designing a mission. Discussion of communication necessitates a discussion on how the communication occurs. In optical communication, information is encoded by varying properties of light. For example, the information can be transmitted by varying the intensity of laser beam. The act of varying the physical properties of light is called modulation. On the other hand, the act of decoding the information in the light by observing those changes is called demodulation. Similar to the RF communication, information can be coded on the intensity, frequency, and phase of light. Light, however, differs from radio waves in a number of ways, and detection and demodulation of light has unique nuances. Now, if we compare RF communication and optical laser communication, optical systems have the advantage of extremely broad, unregulated bandwidth compared to radio frequency system. At K-band frequency of 32, 37, or even 38 gigahertz, bandwidth is typically 500 megahertz in RF systems. But for optical systems, at 1.5 micrometers, the bandwidth may be 1,000 times larger, allowing optical systems to carry substantially more information. For radio frequency systems to compete in a bandwidth-constrained environment, they must resort to bandwidth-efficient modulation for data rates above 1 GB per second, which is neither power efficient nor mass efficient for transmitting terminals. Optical systems typically would have smaller received apertures and lower power efficient transmitters and receivers. A comparison of the burden to a spacecraft by both optical and radio frequency communication systems for data rates of 10, 100, and 1000 megabytes per second and large distance. For comparison drawn, The optical and RF ground terminals were selected to be similar in cost. The radio frequency system selected was composed of 45 12-meter antennas, whereas the selected optical system was equivalent to a 10-meter optical telescope. So already a very huge difference and a very big advantage. Now there are multiple advantages of free space optical system. The major difference between FSO and RF communication arises from the large difference in the wavelength. For FSO, under clear weather conditions, that is visibility greater than 10 miles, the atmospheric transmission window lies in the near IR wavelength range between 700 nanometers to 1600 nanometers. The transmission window for RF system lies between 30 millimeter to 3 meter. Therefore, RF wavelength is 1,000 times larger than optical wavelength. This high ratio of wavelength leads to some interesting differences between the two systems as given below. Firstly, high bandwidth. It is a well-known fact that an increase in the carrier frequency increases the information carrying capacity of a communication system. In RF and microwave communication system, the allowable bandwidth can be up to 20% of the carrier frequency. In optical communication, even if the bandwidth is taken to be 1% of the carrier frequency, that is approximately 1016 hertz, the allowable bandwidth will be 100 terahertz. This makes the usable bandwidth at an optical frequency in the order of terahertz, which is almost 105 times that of the typical RF carrier. Secondly, less power and mass requirement. The beam divergence is proportional to lambda by dr, where lambda is the carrier wavelength and dr is the aperture diameter. Thus, the beam spread offered by the optical carrier is narrower than that of the RF carrier. This leads to an increase in the intensity of the signal at the receiver for a given transmitted power. Now, this is still a booming technology, and a lot of work has been putting into this and developing this. Now, on this slide, I have enlisted 3 missions that have happened, and a few are going to happen in the future. Those missions are DSOC, LCRD, that is going to happen in 2021, and Illuma-T 2022. Now, DSOC is set up for a high definition imagery system. LCRD is to demonstrate power of optical communication, and Illuma-T is the first demonstration of fully operational end-to-end laser communication on the ISS, that is International Space Station. Now let's talk more about the DSOC in detail. Now, firstly, there is advanced lasers in the near infrared region of the electromagnetic spectrum. Secondly, DSOC is designed, it is for 250 megabytes per second from Mars at opposition. 25 kgs of mass, consumes only 75 watts of power, and discerns even faint laser signals and noises. DSOC technologies developed for the project include a low mass spacecraft disturbance isolation and pointing assembly, a high efficiency flight laser transmitter, and a pair of high efficiency photon counting detector arrays for the flight optical transceiver and the ground-based receiver. These technologies are integrated into the DSOC flight laser transmitter and the ground-based receiver to enable photon efficient communications with the capability to discern faint laser signals from background noises contributed by the solar energy scattered by the Earth's atmosphere. Now, DSOC will also require some larger receiver apertures on the ground than the LLCD. LLCD is the predecessor of DSOC. Now, let's talk about the LCRD 2021. It is integrated with 2 optical communication terminals. The LCRD is the successor of the LLCD, where the LLCD's lifetime was limited to the commissioning phase of the LADI mission. The LRCD will be a long-running mission in the geosynchronous orbit dedicated to demonstrating technologies and developing processes that enable high-speed near-Earth and deep space FSO communications. Currently scheduled to launch on STP-SAT-6 in 2021, the LCRD will leverage some components already developed and demonstrated in its predecessor, LLCD. The LCRD will have two optical communication terminals and will demonstrate high rate Earth geo communication, real-time optical relay from ground to geo to ground, power-efficient PPM modulation suitable for deep space missions, high-speed differential shift keying DPSK modulation for near-Earth communications, and performance of network layers and protocols. Furthermore, LCRD contains a high bandwidth Ka band RF module that supports up to 64 MB per second uplink and 622 MB per second downlink, having both high-speed RF and optical trunk lines. The LCRD is to act as a proving ground for technologies to be used on the next generation, and tracking and data relay satellites will act as a bona fide relay satellite after its technology demonstration are complete. Now, what's in the plan in the future? Located in the geosynchronous orbit about 22,000 miles above the Earth, LCRD will be able to support missions in the near-Earth regions. LCRD will spend its first 2 years testing laser communications capabilities with numerous experiments to refine laser technologies further, increasing our knowledge about the potential future applications. LCRD's initial experiment phase will leverage the mission's ground stations, Optical Ground Station 1 and 2, as simulated users. This will allow NASA to evaluate atmospheric disturbances on lasers and practice switching support from one user to the next. After the experiment phase, LCRD will transition to supporting space missions, sending and receiving data to and from satellites over infrared lasers to demonstrate the benefits of a laser communication system. Now let's talk about Illumati 2020. Now it is going to happen in 2022, and it will be the first fully operational end-to-end laser communication system. And it incorporates integrated photonics and a whopping speed of 1.2 gigabytes per second. It will abort the ISS, and it will be a milestone of its own kind. Now, after we have talked about all this, is the problem of communication in the deep space involving the RF completely solved? Well, firstly, laser communication needs high precision. Even the 10th degree change will make the laser to skip its target, and the information will be completely lost. Secondly, it's not independent. It needs a beacon to lock on and then send the laser to its target. And thirdly, lasers cannot penetrate solid objects, unlike the RF waves. And even clouds and mists, laser can be stopped by clouds and mists, so we'll have to rely on the RF waves to transmit if the weather is really bad, or we'll have to develop a vast array of networks across the globe so that we can switch up to another location if there is a bad weather on 1 or 2 stations. So what is the conclusion of our talk today? Well, firstly, we are still far from making a perfect communication system. And the solution? Well, one solution is to focus on quantum communication challenge. Quantum communication relies on the subatomic properties of subatomic particles, where when 2 particles come really close, they entangle themselves, meaning if we change property of one, the other changes instantaneously, and the space between doesn't matter. But It is still in its laboratory phase, and it is very difficult to produce entangled particles. So we are still far from it. It will take at least 100 to 150 years to develop it. On the other hand, the other is to make more powerful optical laser channels and devices. Well, optical laser solves most of the problems of the RF channels. So why not we do that? It is much simpler than that. And these are the references that I took for this slide. And this is our contact information. On the left-hand side is mine. The right-hand side is my partner, Rajat Kumar's. And thank you.